This video is on discussing the average rates of appearances and disappearances of reactants and products in a chemical reaction, and also on calculating these average rates. So this is the continuation of the intro to kinetics notes, and so we're looking at these pictures that show us three containers, and they have a time of 0 seconds, 20 seconds, and 40 seconds, and then in each container, it tells us how many moles of A I have and how many moles of B I have as time has progressed. One thing I should tell you is that these containers are a 1 liter container. That's going to be important in just a minute. So before we can truly tackle how do we calculate these rates, the first thing we should talk about is what can we conclude from looking at these pictures in terms of who A and B are. So it should be fairly obvious if you look at the numbers that at time 0, which means before a reaction has occurred, I have 1 mole of A and I have no B. And then as time progresses, my A is decreasing and my B is increasing in mole amounts, which means that A is a reactant because its concentration, which we'll talk about in a second, decreases over time, while B must be a product because its concentration increases over time. And that's going to be true for any reactant and any product. So looking at this picture, we should clearly be able to decide that this reaction has something to do with A turning into B, okay, as a very generic reaction. So that's the first thing that we can conclude from looking at these pictures. In order to go any further, we have to talk about how do I calculate rate, okay? And so in the what we learned the other day was that rate is measured in the unit of molarity per second. And so what rate really is a change in the concentration over a change in time. Okay, remember concentration is molarity. And most of the, I hate to say time again, in most cases, our time is going to be measured in seconds. And so that's where the seconds unit comes from. And that's why we end up with rate units as molarity per second, okay? Because it's a change in the concentration of either a reactant or product divided by the change in time. So if I were going to look at how A and B are changing, I would go back to this formula in terms of a calculation. Okay, so the only other thing really that we should say is that if A is decreasing over time, we're actually going to denote that with a negative sign, and if B is increasing, we'll denote it with a positive sign. Now, just like energy can't really be negative, it's just the way it's moving. It's the same thing with these rates, okay? We really can't have a negative rate of a reaction. It's just the fact that if there's a negative on my number, it means that it's decreasing with time. All right, it doesn't really mean it's negative. It's just decreasing. So there are a couple of practice problems, and I did not write them before starting this video, so I'll just read it and summarize real quick. So if one says, from the sample data in the above figure, calculate the average rate of A, how it disappears over time from 20 to 40 seconds. And this is actually not a super complicated discussion because we know what my formula is, which is going to be the rate of A is going to be the change in the concentration of A over the change in time. And I'm going to bring a negative sign out in front only because I know that A is a reactant, and so its concentration is going to decrease over time. So my problem specifies that my time range is from 20 to 40 seconds, and so my delta T is my final time minus my initial time, so 40 minus 20 seconds. Okay, remember, just think about like delta capital T, delta change in temperature, right? T final minus T initial, so same thing here, time final minus time initial. And then my change in concentration, I have to go up and look at my picture. Okay, now a minute ago we made a big deal saying that this container was 1 liter. And it's 1 liter because it makes my numbers easy, right? Molarity is moles per liter. But if my container is 1 liter, then my moles will be equal to my molarity, right? Because I would just be dividing by 1. So again, let's think about my time frame here. It was from 20 to 40 seconds. So I'm looking from here to here. What happened to A, right? Well, it decreased from the 0.54 and it went to 30. So I would take, again, final minus initial. So I would take the 0.3, it was 0.3, wasn't it? Yeah, 0.3 moles of A minus the 0.54 moles of A. And again, it's going to come out negative. So I actually really probably did not need to manipulate my rate to be negative because it's going to come out negative. And then I just do the math. So 0.3 minus 0.54 divided by 20 seconds. And so A is disappearing. Oops, and notice I said disappearing because of the negative. A is disappearing at a rate of 0.012 molarity per second. Okay, so that's how I could actually calculate it from looking at a picture. And then 2, a very similar question, calculate the average rate of appearance of B from 0 to 40 seconds. So same thing, the rate for B is going to be the change in B's concentration over the change in time. Change in time here is easy, 40 seconds minus 0 seconds, so that's just 40. And then concentration of B, I have to go back up to my picture. So from 40 seconds, I ended with 0.7 moles of B, and 0, which is where I started at 0 seconds, I had no B. So it's going to end up, oops, sorry about my line there. It's okay. 0.7 moles minus 0 moles. So of course this is 0.7 over 40. And it's going to come out to be positive molarity per second, and it's positive, right, because it is appearing, because it's a product. So its concentration is getting bigger as time progresses because we're producing it in this reaction. So that's how you could look at pictures, kind of do a calculation of how quickly a product or a reactant is appearing or disappearing, and perform that calculation with rate.